Hey, welcome back. It's good to be back at the office. Let's do something very simple today while we prepare for something big next week. I can't help but think that in the last episode that we were together, I think that was almost 3 weeks ago, we were talking about how hot it was.
Oh yeah, man.
You remember? We
Absolutely.
had like an extended discussion on how hot it was,
Right,
and
right,
now
right.
it's like completely wet
Oh gosh, it's so wet everywhere, man.
everywhere. Yeah, and
Maybe we should not complain so much about the weather and all.
Yeah. Maybe we should just not bring it up. Yeah, but you can't help it, man. I mean,
Yeah.
this is a city that is not built for constant rain like this, right? I mean, so and it shows everywhere.
Yeah.
My house is a little bit old, and it's like dampness and everything inside.
Dampness inside. Yeah, we
Yes.
need summer. I mean, sun.
Yeah, we definitely need the sun. All right. That being said, so we've had several suggestions from Twitter and from one of our viewers, Animesh,
On YouTube.
On YouTube. And so what I was thinking today was that while we prepare for that, I have something else prepared. Like this is called as a particle demo, and I think it was shown during the introduction. What you saw in the introduction is what you will see during the result. All right, it's a very neat effect that you can pull off using Canvas and just a little bit of mouse movement and everything.
And some physics.
And some physics. I mean, there's no physics involved as such,
Okay.
but it's just a little bit of trigonometry is what I would say.
Okay.
You can pull off like a very neat effect.
Very
Yeah.
cool. Okay, let's go.
Yeah, let's go for it. So I'll just try to explain what we are doing here. All right. Some years ago, I built this deflection demo thing. This is on my own website. And, what happens is if you have a mouse, I mean, if you move your mouse,
Yeah.
the balls that are, or the orbs that are arranged in this grid try to move out of the way.
Right.
It creates a very neat, effect as such. What I want to do right now is just essentially scale this up to have thousands of particles,
Right.
upwards of 12,000 particles and see what it looks like.
Sure.
There are a lot of inefficiencies built into this demo that I'm showing over here, and I
Okay.
want to sort of improve on this one. This is on my website also. I'll leave a link to this
Right.
on our, in the video description. And and we'll see how we can improve this. So the way this works is that, you basically find the distance from the mouse or to this void over here, just find the distance. And then what you do is you find out where the opposite angle is for a point that needs to sort of get away from the mouse, right? So if you look at this, it's almost as if that point is trying to get away from the mouse. All right. And how it is achieved is just by finding the angle between the mouse and the point and finding the opposite angle and moving into that opposite direction. All right. Now, all the time that is happening, what's also happening is that the points are sort of trying to get back to where they came from. All right. So if they are anchored to a specific point, they want to get back to that.
Right.
And the competition between these two forces is what sort of creates this beautiful demo.
Nice.
All right. So let's scale this up and see how this goes. All right.
Yep.
All right. Let's begin. What I have here is an index.html page on which there is a canvas of size 600 by 600. The index.html also includes a deflection.js JavaScript file. This JavaScript file has two important methods. One is a setup, which occurs when the window is loaded, which is why we have the window.addEventListener, and a deflection. This will serve as our loop function. The loop is achieved using the requestAnimationFrame function. In the setup, we set up the canvas by fetching it from the document using the document.getElementById, and then we resize this canvas if required. We also fetch the canvas, we also fetch the context, and this is used to essentially draw all of our 2D functions. We also fetch the height and the width of the canvas since we will be using it so often during our animation. We'll require a few constants first, namely a padding constant, the number of particles, and the size of the particles, among others. We'll declare the point arrays required to store the particle positions and their anchor points. The particles need to be evenly spaced on the screen, which is why we determine right here how far apart the particles are using the ix and iy variables. Once that is done, we simply create two loops, one within the other, and initialize the particles with predetermined x and y values. Remember that the particle anchor points are the same as the particle points in the beginning. In the loop function, where we also perform our drawing and animation, we loop through the particle array and render it on the screen as circles. Alright, so let's look at what that looks like. I corrected for 2 mistakes. I hadn't declared the spelling of this correctly. And the second thing is that I had used the particle anchors.clone over here instead of particle point.clone because we want to clone the point. Let's see what that looks like. When it is rendered on the canvas, you will see that all of the points are generated or are displayed in a grid quite neatly. But however, nothing happens when I move my mouse on the screen. So let's fix that. We'll first need variables to hold the mouse's X and Y location. We'll add the mouse event message to the canvas, and using the getRealMousePosition function, we'll get the mouse's X and mouse's Y locations. In the display function, where we loop through all the particles, we'll get the distance between the mouse and the current particle. If the distance is within our deflection threshold, we'll calculate the angle between the mouse and the particle's position. With that, all we have to do is subtract pi from the angle radians to get its opposite position. Once the opposite position is calculated using simple trigonometry, we'll set it back to the particle's position. Now that we've added the mouse events and now that we have done the deflection thing, let's look at the result. Now when I refresh the screen, when I move my mouse, you can see that the deflection happens exactly as we intended it to happen. However, because there are so many particles on the screen, we are not able to see changes to an individual one. Let's fix that momentarily. I'll reduce the number of particles to, let's say, just 30 particles, and I'll say that the particle size is about 5. When I say 30 particles, it's 30 rows by 30 columns. It's about 900 particles instead of the thousands that we were talking about. All right. And now you can clearly see the particles getting out of the way. All right. But they don't snap back to their anchor positions. All right. So we can fix that. Let's do just that. Within the display loop, we'll check if the current point is equal to the anchor point. Now remember that the anchor point is the particle's original position. If it is not, we'll simply get the distance between the anchor and the particle's current position, and using a simple normalization mathematical trick, we'll determine the speed at which the particle must travel back to the anchor's location. Finally, we'll also check if the particle is within a snap distance threshold. If the particle has reached this threshold, we'll simply snap back to the anchor's location. Let's look at the results of that. You can see the deflection and you can see the particles wanting to go back to their anchor points. Also observe that once they are within a threshold distance of their anchor points, they snap back. There is one little improvement that yet we can do. The getDistance function uses square root to find the distance, and that's a bit expensive on the CPU. Let's change that to getDistance no square root and see if that improves things. We'll require 2 more constants here that are the square of the deflection and the snap thresholds. We'll replace the getDistance function with the getDistance no square root function. Remember that this will simply return the distance value without square rooting them. Therefore, we must use the square of the distance we want to compare. Let's see what that did. Theoretically speaking, this is much better performance-wise since we are not using the CPU-intensive square root function. Let's set the number of particles back to 120 rows by columns and set its size back to 2. We set the number of particles back to 120 and set the particle size to 2, and let's see what that looks like. This is the final result that we were seeking to achieve. Let's see the results with Ravi. So this is the result that I was talking about, Ravi. So all of these particles are arranged in a grid, and when I move my mouse over it, it's almost as if there's water going.
There is some disturbance.
There's some disturbance in the water. And as soon as the disturbance is gone, the particles will sort of snap back into their original positions.
Very cool.
And this sort of creates a very neat effect. I don't know. Maybe viewers can do something with it.
Yeah. And viewers can just modify the constant values and they'll be able to change the size of things.
The things, make it more pixelated or make the circles a little bit more bigger.
Right.
But as such, this is a nice particle demo.
Yeah.
That sort of causes disturbance and deflections.
Ah.
Teaches you a little bit about trigonometry as such.
Oh, very cool. Very
Right.
nice. Yeah. Very nice.
So that's all we had for this week.
Mm-hmm.
It was just a particle demo.
Right.
Next week, do you remember the game Dots and Boxes that you used to play in school?
Of course.
Yeah, we draw boxes, and if you complete a box, that square belongs to you.
Right.
And things like that.
Correct.
So I want to combine that, and I want to combine the min-max algorithm, which allows the computer to sort of play by itself.
Right.
And by the way, this suggestion comes from none other than Swaroop Sampath. And if you don't know who that is, that was Miss India, I think 1984.
Oh, yeah.
Not exactly sure.
And
but she was
part
the
of that comedy.
Ye Jo Hai Zindagi.
Right.
Yeah.
Correct.
So
How did you?
this happened during a Twitter conversation. So she had suggested, hey, do you guys remember this game? It was called Dots and Boxes. In French, it's called La Pipa Pipette or something like that. Anyways, we'll cover that next week.
Right.
And there you have, and she tweeted that, and I replied, hey, this will be great to implement a min-max algorithm. And she said, yeah, you can perhaps do that. I can teach it to my children or something.
How
like
cool
that.
is that?
Yeah. So next week we'll do that. And we also have animation suggestions. We have it.
Animation suggestion. Okay.
What did I say? I don't know what I said.
Okay.
But anyways,
Right.
one more suggestion was for the
Ray tracing.
For the ray tracing. I had completely misunderstood it for ray marching, which is entirely different.
Okay.
So ray tracing is different,
Right.
which is basically converting your 3D scene into a 2D canvas. So that's a little bit different, and it's a little bit time consuming.
Sure.
But we have sort of put it into our list of episodes that we will do at some
Right.
point in time.
Nice.
Yes. So that's all we had for this week. Do join us again next week.
Where hopefully we get to record. Apparently, there's one more major event.
Exactly.
Predicted
for next week. So hopefully, fingers crossed, we get to sort of record next week, and we'll see you again next week. And thank you so much for the 300 subscribers. Yeah, the big 3.
300. How do I do that? 300.
Yeah.
All right.
All right.
Ciao.
Ciao.